Hello, everyone. Emma, I think we're going to start at sharp so people can get back to their seminars and courses in 1 hour. So I think you can start the recording if you like.
It's recording. You're all set.
Thank you. Thank you. Well, hello everyone, wherever you are in the world. So I don't know if it's good morning or good afternoon or good evening. For those who are celebrating New Year, Happy New Lunar Year, I guess. And welcome back to the second session of the 2026 Space Economics Seminar, jointly organized with the Ownership Project at the Harvard Business School and with the European Space Policy Institute. As I mentioned also last month, we will continue this semester and we'll continue our meetings monthly, every month until May, including in May. And this is, of course, with the support of HBS and SP. And we have a full slate of speakers from both sides of the Atlantic. So I'm very glad about that. I will remind you the seminar guidelines. So please keep your microphones muted unless I call on you, and post your questions in the chat. So I will take them after our speaker finishes the presentation. Please don't interrupt the speaker while they're talking. And this session is recorded, and Emma sent it to a form to fill out to give us consent for this recording. If you didn't fill it out, please do it right now. And of course, we expect the participant to read the paper in advance. Emma usually sends you the paper a week before the meeting, so we can have a very productive discussion during the seminar. That being said, it is very nice to have with us Alessio Terzi from the University of Cambridge today. So we started with US, now we moved on the other side of the Atlantic for this meeting. And he will present his paper From Sputnik to Starship, Estimating the Learning Curve of Space Launch Technology. And the paper analyzes how space launch costs have declined over time through learning by doing and technological progress, showing that cumulative experience has been a major driver of efficiency and cost reduction in the sector. It also discusses market structure, geopolitics, and sustainability challenges, which may shape future innovation trajectory. And let me very briefly present the speaker, Alessio. So he is an assistant professor at the University of Cambridge. He's also an adjunct professor in economics at Sciences Po in Paris. He's a member of the World Economic Forum Global Future Council. And prior to this, he was an economist at the Director General for Economic and Financial Affairs of the European Commission. And among other things, a fellow at Bruegel and also a Fulbright scholar at the Kennedy School. So it's very nice to have you, Alessio, here. And I will give the floor to you. You have about 30 minutes, and then I will let the participants to ask questions so we can have a little bit of a discussion. The floor is yours.
Thank you. Thank you, Joanna, very much for the introduction. I'll try sharing my screen, hoping it works as before. You tell me if you can see it. Good. All right. So
Good, it's fine.
great. Thanks a lot for the invitation. I'm very thrilled to be talking to what I consider the paramount setup or meetup for space economists across the globe. It's important to say, this is joint work with my partner in crime, Francesco Nicoli from Politecnico of Turin, whom I believe is in this call in and out, but he told me he would attend and he might jump in for specific answers later in the second part of the seminar. So I guess I will start, to give you a bit of a introduction on motivation. I'll be brief on that, given the audience. Give you an overview of this paper is based on a novel database that we've assembled. So I'll say 2 words about that, and then show you what we've done with this new data set that looks at launch costs, as Joanna was mentioning. And then I will show you a bit of the analysis we've performed. All of this, again, it's worth mentioning, is based on a paper that is not published yet. I mean, we're hoping for it to see the light soon, but these results are unpublished for the time being. The motivation, I mean, the starting point is a bit a paper that I wrote with Francesco Nicoli 2 years ago. And what the paper was doing there was to say that at the end of the day, we should think of the interaction between Earth and space through trade economics lenses. And so that rather than look at space as a sector, we think of it a bit more in trade terms. And if you look at it in trade terms, you have 2 places that exchange goods, services, investment, and so on. And what you have in between the 2 places is a transaction cost, a cost of transport. You can call it a gravity tax or a gravity tariff, whichever way you want to perform this parallel. And so it becomes very important. It became very important to us. That was more of a theoretical paper, but it becomes important to then think about how these costs have been evolving, and crucially, how these costs will evolve in the future. We know intuitively, you will all know in this call, that the costs of accessing space have dropped, but we wanted to understand first by how much, and second, how is this big, and third, is this likely to continue? And this is important, and here, in a way, I'm linking it to something that Max Roser of Our World in Data was saying, referring it to general technologies, so not to space specifically. And the gist of this quote is that technologies that scale are the ones that will matter in the future, because if you scale, the costs go down, and if the costs go down, something can spread, and if it spreads, it becomes a predominant technology. And I think that people in this call believe that space is one of these technologies that will spread, that is already much more important than it was a few decades ago, but it has a lot more potential than what we are seeing. And we wanted to add flesh to this general intuition, or data to this general intuition. There is a bit of literature. I mean, in general, as you know very well, the literature on economics of space is too scant, given how important the topic is, we believe. In general, there has been a bit of work that has been looking at historical estimation of costs and how they have evolved. And there is a paper by Adilov and others in 2022 that looks at some aspect of this. Corrado and others more recently on PNAS have some estimates of the average cost trend, but we're sort of taking this analysis further and bringing in also a learning curve dimension to it, which is something that has been done for other technologies, but not for space. Of course, there is a literature that is non-economics, economicsy, or economics related. There is an engineering literature that has tried to estimate the costs of various rocket categories, but because it's an engineering literature, is less interested in average costs, which is what we're interested in from an economics perspective. They're interested in the specific rocket category or family, and then it's a different type of exercise. So what we've done is that we've collated and standardized data on cost of launches per kilogram. We've standardized it to in terms of dollars. We've brought it to 2024 dollars, so actualized it. We standardized it in terms of making everything Leo or Leo equivalent. We've looked across countries, and we've pulled all of this data from a variety of sources. And what we have at the end is over 4,000 launches that took place between the last six decades, basically, for roughly 1,300 different rocket configurations across the major spacefaring entities or geographical groups. Now, I usually have these slides. Many of the initial ones you will have seen, so nothing particularly radical. It's just to show, that our data matches what you will have seen elsewhere. You will know intuitively. This is on the total number of flights that we know has been exploding as of recently in the SpaceX era. So to say, we can obviously look at it by mass. And so we can see effectively the same chart, and we see that mass to orbit is exploding. But again, these are charts that you will have seen. Where things can start to get interesting, given the database that we have, is that then we can, look at things like the average mass of rockets, and so you can start seeing a bit exploiting the granularity of our data set, and you can start seeing how the US has focused more on super heavies or larger rockets, how India has focused on smaller payloads per rocket or rocket categories. And again, this is just to give you a sense of the granularity that our data allows. And then this is the chart that you were sort of all waiting to see, given the title of this presentation, which is the average cost of launching 1 kilogram into space or into low Earth orbit or in low Earth orbit equivalent. And so in our estimations, this is something that goes from an average of 87,000 roughly in the 1960s, late 1960s, to roughly 3,800 in 2024. So obviously, this is a very large reduction in costs. Again, this is where we are sort of replicating things that you might have seen. And Corrado, I was looking at Corrado and others recently, and they have a similar chart. This is where, however, things start to get interesting, because as I said, we can go beyond, we can look at the granularity and exploit the granularity. And we start seeing some interesting patterns, because what you have here on the left-hand side is the cost per launch, and each dot is an individual launch. And so aside from the average, once you unpack the average, it's interesting to see the variance. And so to see how there was a very large variance, and the variance has sort of collapsed. Now, there could be different things that are at play. It could be, as we suggest, it could be that it's a Cold War effect. And the reasoning there is to say, look, in a Cold War type of mindset or setup, you launch because you need to launch, or you want to launch and you want to show technological prowess, you want to show a variety of things. The cost is sort of a secondary dimension. After the Cold War, you start launching more if it's economical, and second, you can start using launchers of others if it's a cheaper alternative. Again, in the recent past, a variety of satellite companies I've been engaging with would say we launch with SpaceX. Of course, it's the cheapest, and we use that. And there hasn't been this geopolitical dimension so much at play. It could also be that this is a technological story. So we know that early on, technologies have wider dispersion. And this is true for all technologies, because there is still experimentation that is wider. And so, as things consolidate and there is a sort of an understanding that certain applications work better than others, then you would expect to see this collapse of the variance of costs of launch. The next thing that we do is that we wanted to estimate whether space respects Wright's law, and so whether there is a learning curve of space as we see for other technologies, and whether this fits the data. The particularity of Wright's law, you might or might not know, is that it sort of finds or it postulates that there is a relationship between costs and cumulative launch in this case, or cumulative production for other technologies, and that this reduction is constant in percentage terms. And so we sort of we see whether our data fits this relationship, and it turns out that it fits incredibly well. Perhaps it shouldn't have surprised us, given that Wright's law was developed for the aerospace sector to begin with. So Wright was working on planes in the 1920s, I believe it was, or 1930s. And so, you know, it seems that space and rockets have been following this law. What we find is that for a 1% increase in cumulative mass sent to space, we observe a 1.2% fall in the costs. Now, this is interesting per se from a technological perspective, but you might be wondering, okay, but what does this mean? Like, is 1.2 big or small? And so this is what we were trying to get at for the rest of the paper, or for the next a few slides. And what we do is twofold. First is that we make a historical comparison to other transport technologies of the past to say, okay, how does this compare to past technologies of transport technologies that were, had major repercussions for society? And second, how does this compare to other current technologies that are known to have very fast, steep learning curves? So for the first part, I love these historical parallels. I hope you bear with me. But what I did is that I downloaded data for basically freight costs, historical freight costs. And what I wanted to see was how this compared with the introduction of the steamer. So we're talking of the 1800s, early 1800s, and something a technology that has sort of paved the way for the first wave of globalization. Again, bear in mind that we have very much this trade mentality or framework that we read space with. And so that is where the trade parallel was interesting to us. So we download some data for cotton, for wheat, and how the costs evolved in the aftermath of the introduction of the steamer. So that's what you see on the left-hand side. On the right-hand side, you have, again, the same chart you saw before. It's just that now it's 5 years rolling average to smoothen out the variability. And because it's normalized to 100, the only takeaway you should get out of this comparison of the charts is that the chart on the right goes to a point that is lower than the chart on the left. And what this means is that over a comparable period of time, the reduction in costs of sending 1 kilogram to low Earth orbit is lower than the reduction in costs that we saw for some merchandise or for cotton, for wheat, following the introduction of the steam. So this is one thing that we do. You can test it more statistically, and we show that it's indeed happening faster in the case of space than it did before. You know, effectively, what we're testing here is something that is closer, where if you're technologically minded, to a Moore's law. So we were speaking about Wright's law before. What Moore's law is that it postulates that there is a relationship between the cost reduction and time. And so what we're seeing here is that the speed the pace of Moore's law was faster for space than it was for after the introduction of the steamer. So this is what we did. The second thing I told you was related to other technologies, let's say concurrent technologies. And so what we said is maybe because we were chatting with Joanna that I have also another hat. I normally also work on climate change and green growth, and this has been one of the topics I've been working on. And I'm constantly exposed to this idea that solar PV is is amazing because it's a technology that has scaled so fast because the learning rate is just incredible, and this is a bit what these charts show. And so on the left, you see that the price declines have been very fast, and on the right-hand side chart, you see that this has been faster than the reduction in other renewable technologies. So what we said is, okay, let's pull data for solar PV. We compare it with our data on space, and we see how the cost reduction has been. It has been normalized. And indeed, you see that the chart on the left actually now goes much lower than the chart on the right by the end of the time series. And what this means is that cost reductions in space have been more pronounced. Okay, so over a comparable period, actually the same time from 1975 to today, the cost reduction in solar PV has been sharper. But what we're interested in is the learning curve or the Wright's rate, and so it could be that space has scaled less. And so, yes, the reduction in the cost of accessing space has been less pronounced, but because the scale hasn't increased as much as solar. And that is indeed exactly what we find. And what you should see in this chart is effectively that the slope of space, so the one on the right, is actually steeper than the slope of solar PV, which is the one on the left. Now, this is not immediately evident. If you just look at it, we can test it statistically. And indeed, that's what we find, that there is a statistical difference and that space, the learning rate in space is faster than what we have observed for solar PV, which we find is quite something. Now, one interesting thing, and this is where we were pushing a bit the logic of the exercise we had run, we could stop there, but there is this interesting principle that, because reductions or cost reductions seem to follow this empirical regularity, you can use the empirical regularity to project costs into the future. And indeed, there are papers that show that using Wright's law is what produces the best cost forecasts for a variety of technologies. And so what we say is, given that we are approximating, with an R squared of 0.94, so our data very closely follows a Wright's law. Why don't we exploit Wright's law to project costs into the future? Given that this is, we're trying to get at whether space might have observed these steep learning rates or these steep cost reductions, but we might be at the end of it. And so, we go about it in two ways. The first way is that we produce the scenarios. And so effectively, what you have to feed as input is assumptions on how much mass will increase or how much demand will increase. And the increase in demand gives you a projection allows you to project how big further cost reductions can be given the learning rate, the technological learning rate. And so we produce a set of conservative, central, or bullish estimates, and then we adopt a data-driven approach, and I'll tell you more about it in a few slides. So in our central scenario, what you get is that the average cost of bringing 1 kilogram to low Earth orbit could drop further from 3,800 roughly, which is where it was in 2024, to 1,800 by the end of this decade, and could go as low as 400 by the end of the next decade. And this is our central scenario. This is, the chart on the left shows you what cumulative mass has been up until now, and then what our scenario is, and then we're fitting the data. Well, let's say we are inputting the data on the left into our rights law, and that allows to produce estimates for costs. You can do, as we were saying, a more conservative scenario. I will not go into the details of, we can go into the details of how these are created, or a more bullish scenario. And they produce certain estimates. We are going to look at them in aggregate in a second. But of course, you can't stop me here because Joanna told you not to interrupt me. But in a normal econ seminar, immediately people would jump on me and say, "Look, but you've created these quantitative estimates. How do I know that you and Francesco haven't been cooking these numbers by just producing some estimates to get these costs to go down?" So we were like, okay, fine. What we're going to do is that we're going to create an entirely data-driven projection of cumulative mass. And effectively, this is using a time series forecasting method, which looks at how cumulative mass has been evolving, and then it projects it into the future. And this, again, is entirely data-driven. And then once we take that, we can input it into our rights law and get some cost projections. So this is how it looks like. It looks much more conservative, even than our conservative estimates. And I will actually say one word here about this, which is that, forecast, something that is intuitive, but it's worth underlining, is that forecasting at times of structural breaks is very hard. And I showed you at the very beginning, you had these charts of cumulative mass to orbit, or mass to orbit actually, and we were talking about the SpaceX era and how the growth of mass to orbit has exploded over the past 5 years, basically. And so the problem of forecasting in a very intuitive way is, if you average out the growth rate of cumulative mass to orbit over the last 30 years, okay, of course you get something that looks much smoother. But then, is this the right approach? So you are saying that what we've seen over the past 5 years is a blip, and it's something that is going to smoothen out and go back to a very sluggish growth rate. Or you can sort of put much more weight over the last 10 years or 5 years and focus on that. And then if you do that, that's when you approximate our bullish scenario. Of course, if you go in the very bullish scenario, you're focusing, on the last 3 years of growth, and their growth rates have been, something like 20% on average. And so what we would be projecting is that growth enters into a hyper exponential phase very quickly. So this is everything that is happening behind the scenes. I'm not cooking the books. I'm not hiding anything, but this is what is happening. But what we find interesting is that even in this ultra conservative scenario, costs continue to decrease, and they go below 2000. Probably, as a point estimate already just a few years after 2030, and they go well beyond by 2040. This is fundamental. Again, I used to stress this in lectures or at seminars. I don't think I have to do it here. But again, we're not talking, 100 years from now or 50 years from now. These estimates are for the end of this, for the end of this decade. And 2030, 2035 or 2030 especially, these are within an investment horizon. So you can go and talk to a company and present these numbers, and this starts to be important and relevant from a business perspective. This is the chart I wanted to show you. I wasn't showing you the point estimates before because I knew this chart was coming up, which is a comparison under the various scenarios of the cost reduction by 2030, or the point estimate of the costs by 2030 and then by 2040. And with a dashed line at the 2000 level and the 1000 level. So just to say that whichever way you slice and dice the data, whichever assumptions you make for the future evolution of mass to orbit, the reduction is going to continue and is going to be significant. And the reason for this, you might be wondering why that is the case, is the steepness of this learning curve, and the fact that the learning curve is defined in percentage terms. And so because it's steep and because it's defined in percentage terms, it means that, early on, just by virtue of continuing this pattern of sending mass to orbit in a significant way, you're going to observe some significant cost reductions. And then whether further down the line it explodes or doesn't explode quite matters less for cost reductions, because the realizations happen early. We have to robustness test. We performed a robustness test on these estimates, and so we did a so-called placebo test in time. So we pretended that our data was finishing in 2025, and then we used our methodology to sort of backcast or see how good our methodology would have been in foreseeing cost reductions. As a matter of fact, it looks like it does either a good job or a conservative job. So at most, it would suggest that our methodology should be taken as a conservative estimate rather than an excessive estimates of cost reduction. So this is more or less what this is, which is we expect, we observed or we track, we show how space has experienced very fast learning curves. This implies to us, to go back to Max Roser's initial quote, a bit the motivation of this paper, is to say space scales. And crucially, there are no indications that we are at the end of the cycle. And so this is, again, very important from a business perspective, and I guess for everybody in this virtual room, because it suggests that space has a further scope to increase. And the fact that the costs are going down, again, it's probably obvious to everybody here, but it means that more and more applications of space might become profitable. And so things that we've known about, but that were not happening just because the financials just weren't adding up, might start adding up, because there must be a cost point where they do. And there's the classic examples where it's data centers, where it's advanced manufacturing, where there's specific pharmaceutical products. This is stuff that has been talked about for quite some time, and we are not seeing it yet, if not in experimental phase. But we will see. We suggest that this data sort of pushes the argument that many of these applications will start becoming profitable sooner rather than later. I think I'm more or less at 30 minutes, so thanks a lot for your time.
29 and 30, so very impressive. Thank you so much, Alessio. Thank you for the presentation. And you have a ton of questions and comments, and I'll try to go in the order in which they were written in the chat. So, Mark, you are comparing Alessio results with Matt's and Rousseau's book. And would you like to ask your question, or maybe ask specific questions to Alessio and Matt, since they're both here to defend their results? Mark, would you like to? I can read your can you do? No. Okay. So okay, I'm gonna read the comments. So Matt and Rousseau's books and paper, they suggest that cost would drop to $100 per kilogram for Starship, but this does not seem to fit with your findings. And I was wondering if Alessio and Matt can comment.
So there was one slide that I ditched out of this deck, but it's worth mentioning it now, which is what I call a smell test. And that is our reality check. And that is, okay, I've done all of this data analysis and all of this econometrics forecasting or whatever. But how does this square with what we know? So, on the ground, how does this look like? And in a way, this links to Starship because I was showing you data for average costs. That doesn't mean, but obviously we're focusing a lot these days, not on the average global cost, but on the cheapest available alternative, which tends to be with SpaceX. And SpaceX already can launch at some of the costs that I forecasted into the future, they can already do right now. And the bet then is, what is going to happen with the introduction of Starship, if and when it gets introduced. And there, reductions can go very low. It depends on how often you think that this thing can be reused. And so they could go as low as 500 or even less. You're saying even lower than that. An interesting exercise. I'm not presenting it here today, but obviously our data allows to split the data. So to say, can we focus only on the US, for example, and perform a learning curve only for the US? And we do that. And we can show that the learning rate is very fast, is even faster, obviously, than the global average, in part, or actually because of SpaceX. And that suggests that the costs can go down even further, much further for the US by doing this empirical exercise, focusing on that country alone. But
Great.
Marco, if you want to say something, go
Matt,
ahead.
would you want to add something to this?
Only a small thing, which is that ours wasn't an analysis at all. Certainly not as sophisticated as this. We were just saying, what is Elon promising? And he's promising a number like 100 or two. So either he did this analysis already, or you guys are formalizing what he was promising and intuiting, which is really great. Awesome presentation, by the way, Alessio. Thanks a lot.
I guess just to add, the reason why we were trying to do this exercise, especially the forecasting part, is that, as you were saying, Matt, there are a lot of these estimates out there. Now, Elon makes his own, but there are these estimates, and we were trying to add a bit of technicality to it, because if not, it feels a bit like, I think that it's 150, I say that it's 300. And then it's very hard also from an investment point of view to say, okay, but how grounded are these numbers? And that's what we're trying to get at.
Great. Thank you. Mehdi, you had some question about the specific assumption. Was that clarified during the presentation?
Oh, thank you very much. Thank you for the presentation, and thank you for organizing. I think my both points was mostly about definitional clarity and the constructs that you used here. Because in first what you were referring to as space, to me, it sounded more like we are talking about cost of access to LEO. It's not necessarily stands for space. If that's the assumption, that was the first comment. And the second one, which I think is a similar thing, was about the comparison you made with another technology. So you compared the cost of access to LEO per kilogram over time, comparing it with the cost per unit of another technology in a different time slice, in a different setting. To me, it seems that there might be fundamental differences between the two of them, like how institutionalized is each market, or how capital intensive is each, or that might impact the whole comparison. And I'm not saying it's not a good comparison. I'm just saying like it's easy to attack in both cases. But I really appreciate the presentation. I enjoyed it very much. Thank you.
Thanks a lot. I mean, on LEO, we're not arguing that LEO is the end of space, and actually it's more of a technical assumption, as in a standardization. So there are rockets that are sending to GEO, there are rockets that are sending to other places. We are standardizing that to LEO only so that you have estimates that are consistent throughout the data set. Because if not, you have one rocket that sends in one place, a rocket that sends in another place,
and it's harder to compare. And so we've just standardized everything in Leo equivalent so that you can compare which one was cheaper, but we're not, that our analysis doesn't force anything in saying, Leo is the end of space. By the way, to do that, we've used some standard engineering coefficients. It's very transparent in the data set. It will say where this standardization has happened, and so you can see for which rockets it was applied. For the comparison with different technologies, yes, I mean, it's a point well taken. It might be a bit of a stretch. I think it's a useful exercise to put things into perspective, but a variety of assumptions and data, data assumptions go into it. I was using historical data for cotton from the 1800s. Chances are that these are estimates that are very rough. If you're comparing it to solar PV, I was presenting this paper at the Institute for Manufacturing here in Cambridge a few weeks ago, which is like a place of engineers, and they're like, okay, but let's go into the details. How can you say that a rocket is the same as a unit of solar PV? There are different technologies, and so as a result, the cost reduction, one can be more standardized, the other has so many more components, so it's much harder to standardize, and so of course, and this is only on the technical aspect. You're hinting at market structure and a variety of other things. So of course, these are different technologies. We find it striking that all of these arguments should stack against the space, so should be in favor of solar, should justify why solar is faster, and we don't find that. At least in terms of learning. And so again, I still think that it's an interesting point. That being said, of course, a spin-off of this project could go more into the details of saying, okay, but why have we been experiencing these cost reductions? So what is it exactly that is at the heart of it? Is that change in the type of rocket? Is that change in the family? Is it tinkering and improving on elements that were already there? And probably it's a variety of these things, and the granularity of our data allows to look into the details of it.
Thank you, Alessio.
Thank you.
And Mitchell, would you like to ask your question about CapEx into R&D in this space launch market? Are you still here? So he's asking, okay. Did we get no? So he was wondering if you had considered analyzing the behavior of CapEx into R&D in the space launch market with emerging markets. There have been a few examples of substantial R&D CapEx, which may cool as space economy approaches equilibrium or may show an ever-increasing trend as the market develops new possible sources of revenue, just as some possible insights which might have been developed. So that's Mitchell's question in the chat.
I mean, no. The short answer is no, in the sense that I mean, I would say one thing, and I was having this exchange with Luisa Corrado via email. But in a way, we're focusing again in line with what has been done previously on unit flyaway costs. We don't bring into the picture the R&D costs of developing the rocket per se. There are reasons why this might be a bad idea and reasons why this can be a good idea. We don't even enter into that debate. We've tried to standardize a data set and then eventually make it available to everybody to experiment, to improve, to complement potentially. But we haven't been looking at investment in R&D specifically. Mm-hmm. And so, I mean, I can't say anything on the past and even less so for the future.
Mm-hmm. And speaking of Luisa, she has two questions. Maybe one of them you answered. Yeah. Would you like to ask one or both of them, depending on which one it remains unanswered, Luisa?
Thank you, Alessio. First of all, really enjoyed your presentation. I think, I can leave the first question because you already responded. So it actually is exactly on the definition of a unit flyaway cost. So of course you are excluding research and development. And so since you're spanning different era, let's say, different periods, so from the Cold War, government programs up to the modern commercial providers, clearly this may be an influential element in the computation of your cost. So maybe in the future you can define a robustness or robustify your economic image, if possible at all, of course. The second is actually on the right law that you are estimating. So it's the relationship between mass and unit flyaway cost. But I mean, my question is, are you considering also that be again, you're not necessarily picking up learning by doing, purely learning by doing effect, but there could be, for example, compositional shifts, I don't know, entry and exit of firms, different market structure in different areas, and more importantly, reverse causality. So it's true that an increase in the mass will lower the cost, but it's also true the opposite, that lower cost will lead to higher demand, and therefore this will actually lead to an increase in more cumulative mass. So this reverse causality effect is there. So from lower cost to higher demand to higher mass. And so this reverse causality may actually create some, again, interpretability issue in the figures that you have. These are my questions.
So one thing, I'll start from the end, which is on the reverse causality, supply and demand, which is, let's say, a well-known issue within the technology literature that uses Wright's law and estimates learning rates. I mean, there's no claim of causality to a certain extent. So we are tracking an empirical regularity and we're projecting it into the future. This is a supply side story by virtue of how Wright's law is implemented, and there is no demand side. And to an extent, at the end of the paper, or I think of the slides, what we're suggesting is that the demand side is missing. And so we would need a model to estimate demand or demand potential to bring the two analyses together. And it's a fair point. The other very fair point is on market structure, which it's something that is very interesting to me, and it is something that I'm planning to have as an extension of this paper. Again, we have the data, and we can start looking at whether the market structure and ownership structure, how this, if this has a relationship with different phases of the price of the cost reduction. And it opens up a gap between cost and price. By the way, I said the cost and prices. Of course, if you're in a monopolist situation, as might be now the case, or increasingly the case, especially in the US, or not, this would have repercussions in opening up a gap between costs and prices. So all of this is something that we're planning to do. So, point very well taken, evidently.
Thanks.
Thank you, Alessio. David, you have a question about geopolitical tensions and the Wright law. Would you like to ask your question? I saw you recently on my screen. I know you're still here.
Yes, I'm happy to. And so this really just came to mind as considering the way that your charts are tracking the decreasing cost during Cold War tension and the way that it went. With the rise of SpaceX, of course, we see massive differences in that. So what I'm wondering is whether you have considered at all the return that we are seeing today to geopolitical tension and how that might send us backward and actually prevent the development of Wright's law moving forward, and how that's impacting the market.
So great, thanks, David. It is in the conclusions or in the discussion part of the paper, because it sort of links to the chart I was showing at the beginning, which is, I was telling you, at least if you buy the story, that you had greater dispersion of costs when you were in a Cold War period, and then that reduced afterwards. But if that story is true, we might observe a widening of dispersion again into the future. And the mechanism would be as follows, which is, it might be true that it's cheaper to launch on SpaceX, but that might be seen as a vulnerability, let's say. The fact that you're entirely dependent on a provider for access to space that is in a country, and that the president of that country might say one day, you know what, because of whatever reason, you're no longer launching with SpaceX. If you don't have your own launch capacity, you are stuck. And so it might be that countries decide to say, you know what, we're going to send with ours, even if it's costing 5 times more, we still send with our launchers. And so we might observe a widening of that gap. So a return, as you were suggesting, to this period. I take the opportunity to announce a sort of a spin-off. It's another paper. Maybe I'll come to present it another time, but it's the geopolitical angle to this paper, sort of leveraging the same data. I was hinting at the fact that we can compute learning rates by country. It's something we do. And we can project it into the future. It's something we do. And we can show this gap that you're alluding to, which is, the gap is now widening. And obviously this has policy implications, because it means that, yes, you will continue having access to space if you're another country, but this is going to cost you a lot. And so this is something you want to plan for into the future, or think about into the future.
Thank you. Thank you, Alessio. And Akhil has 3 technical questions. If you didn't get an answer during the presentation, would you like to ask all 3 of them, or maybe just the ones that did not find an answer during Alessio's presentation?
Yeah, sure. Thanks, Alessio. Can y'all hear me? Yes.
Yeah.
Yes.
Great. Yeah, thanks, Alessio, for this presentation. I think I have a few data questions, but also a question about the specification here. So just on the data side, I think I put this in the chat, the early period costs, it's not clear to me, I guess, how you constructed them. In what I've seen publicly available, and indeed in some of the work that Luisa and I did on related subjects earlier, the per flight costs are backed out from sort of overall life cycle cost estimates in the budgeting process that include R&D estimates and also integration cost estimates that are not often included in many of the sort of later period estimates because of how the pricing worked that the government was charged that was then worked into sort of the public cost or price estimates, however you want to think about that. So because per flight cadences were used in those early periods to derive some of the costs, it seems possible that unless you've sort of reconstructed those per flight costs from original budgets without using the flight cadences, there might be some circularity in there in which sort of mechanically you're going to see a learning curve appear because those costs are decreasing sort of as recorded mechanically as a function of what was launched. There's sort of a similar question that I have there for Starlink and kind of the more recent Falcon era launches. But this gets to sort of a broader question, which is how you're thinking about the learning curve. In the example in the paper and that you threw up on the screen earlier, I didn't pay close enough attention to the subscripts to see, I guess, if you're estimating these learning curves with sort of launcher fixed effects or launch operator fixed effects, or even launcher specific learning curves, right? Because logically, just given the structure of the industry, one might think perhaps that, for example, SpaceX is getting the benefits of the learning curve. It's hard to see why Rocket Lab or the Indian PSLV launcher should be getting the same benefits from that cumulative mass launch, right? Like these are disjoint labor markets. ITAR and other export controls limit sort of mobility there. And so I think just mechanically, it's a little bit hard to understand what the learning curve means, given sort of the data issue and this international piece. And then I guess the third question that I have is like, what is the Y variable that you're using, the left-hand side variable? Is it raw dollars or is it measured as dollars per kilogram?
Yes. So it's dollars per kilogram for the Y variable. For the learning curves, it's a good point. It sort of links to what I was saying before, which is, and the discussion I was having at the Institute for Manufacturing, where people were saying, okay, you're showing us the general pattern. It's nice, but like, tell us why. And so it sort of goes in the direction that you are hinting at, which is, okay, but is it within family? So is it within the same family of rockets that things are becoming better, or is it a change in the type of rocket? We we see some elements of that. So one thing that we did is that we performed a structural break analysis. And so we computed our learning curve or Wright's curve. And then we asked again, let's say the data, we let the data speak. And we said, okay, if there is a structural break in the pattern, so an acceleration in the rate of learning, where would you place it? And it so happens that it's exactly around the time of the beginning of reusability with SpaceX. So I think it's 2010, 2009, something like that. And this was interesting to us because it sort of lends evidence to this idea that, learning curves matter or change when there are these quantum leaps in technology. So this is something that goes in the direction of what you're saying, but, again, what I was saying before is it could be done in a much more granular way. So we could cluster things by rocket type, or we could run it, as you were saying, from an econometric perspective with fixed effects by family of rocket type. That's something that can be done actually very easily, and we haven't done that yet, but it could be done.
Yeah, I think probably the more interesting thing to do would be to run it with the Y variable just being the raw dollars instead of dollars per kilogram. It seems like perhaps with dollars per kilogram, there might again just be a mechanical correlation here, where as the mass being launched is increasing over time, you're just going to see what appears to be a learning curve purely because of how the Y variable gets constructed. So I think probably that would be a more interesting test, I think, in my mind, and relatedly, also try running it without SpaceX at all in the picture, right? Because there's some, I think, important details happening there with the market structure that perhaps may be worth breaking out.
It's something, it's something that comes up very often, this thing of saying, okay, but how much is driven by one company at the end of the day? And the problem is that one company is very big. So to just run the data without that one company seems odd. So to ignore it, but I understand what you're saying. And in a way, it sort of affects our future estimates as well. Because if for whatever reason, SpaceX goes bust or stops functioning well or whatnot, all of our exercise probably is going to look very different into the future. And so also from a projection perspective, because by now, I think in our estimates, it's like 96% of mass to orbit for the United States in 2024 was due to SpaceX, which means that, that one company is whatever happens in there is the determinant of how prices are going to evolve into the future.
Yes. And so this, I guess, gets to the last piece, right? Which is like, you're thinking about sort of the Starship era. I think it's probably worth doing one more layer of standardization to standardize access to a reference altitude, like say 250 kilometers. And the reason I say this is because, does anybody know, I guess, how high Starship can go in a single flight? Like even when it's working? So it's like 300, right? Like it can't reach most of the altitudes in LEO just as a physical restriction on how the system works. There's a bunch of these other launchers there too that have these kinds of restrictions, like Electrons can't get that high, right? So it's probably worth thinking about how you standardize that just so that you can make sure that for the projection, there's sort of apples to apples comparisons happening. But anyway, thanks so much. Super cool work. Really appreciate it.
Thank you very much. And thank you, Alessio, for a really great presentation and for all of you to ask so many good questions. I know that there are 27 more that we are not going to go through, but I very much appreciate you being so so involved in this talk. I want to remind you that the next meeting we're going to have, it's going to be on March 26th. It's going to be a surprise what speaker we have. It's going to be a surprise because I'm still finalizing the schedule. So if you haven't heard back from me, it's not because I forgot you sent me an abstract. It's just we're really finalizing the schedule. If you heard back from me, that's good. And then the next one is going to be April 21st, and the last one is going to be May 29. Again, we will finalize the schedule. We really received a lot of abstracts, and there are a lot of very good papers, and we're very, very pleased about that. And thank you for your patience. And again, thank you for showing up every month and being so active into this discussion. And I hope we'll continue this in the same spirit also next month and the months after that. I wonder if Matt or maybe Mattia would like to say something at the end of the session. If not, that's all we have. Yeah, Matt, please.
Well, thanks to Alessio for an awesome presentation and to everybody for the comments. This was another great session, and I think this really is turning into a vibrant community of economists working on this issue, which is so exciting to see and real proof of the idea that Ioana had to launch this, and really excited about it going forward.
Niha, maybe also. I saw you now. So
No, I
would you like
just want to echo what Matt says, and we really appreciate everybody's interest. And it's great to see everybody here. And so please let's keep growing the group. Because I know we had some newcomers today too, so that'd be great to have even more. So thank you very much.
Lovely. Mattia, are you still there or
Yes,
with
I
us?
am.
Hi.
Thank you very much to Alessio in particular and Francesco for the work and the presentation today, and of course to everyone for joining. And looking forward to the next seminars, and fully echoing what Matt and Nina said. So I think the fact that we're collecting this community here is probably the original reason why we even started this. And I think seeing this taking shape is really a great step in the right direction.
Thank you. Okay, well, thank you everyone, and happy year of the fire horse, I guess, to everyone. Okay, bye.
Bye. Thank you very much.
Bye bye. Thanks for all the comments. Bye.
Bye, thanks.
Bye. Thank you, Alessio. Thank you, everyone.